Lorentz boosts with quaternions is a very short paper, just barely gets over 1 page, available at the preprint server at visualphysics.org. It addresses what I consider a legitimate complaint about using quaternions to do work in theoretical physics. And that is that there isn't an elegant way to represent the Lorentz group. Now, the Lorentz group shows up in so many important and critical basic areas of modern field theory that if you don't have that, you might as well not work with quaternions. And that's the way it is. There are no international meetings involving them. You know, all you need is like one critical flaw, and that's it. So you say, well, didn't people try? And as a matter of fact, folks tried in 1910 and 1911, and they found an answer by throwing in an extra factor of I, which makes them no longer quaternions, they're biquaternions. We had to go all the way to 1995 before a fellow named De Leo figured out how to use infinitesimals to do it. But that still doesn't quite feel right, because what we expect to see are hyperbolic cosines and sines. Well, I thought maybe I should give this a try, because what we do know how to do with quaternions is 3D spatial rotations, and special relativity is just supposed to be rotations in space and time. Now, how do we do those 3D spatial rotations? Well, the formula is really simple. Wrote it up right here. Okay, you just hit it in front and in back with this cosine and sine sort of thing. The one with the star is actually involving a mirror. It's a conjugate operator, but it really is doing the same work as a mirror. And I think maybe that's why in the end it ends up using this double angle formula, or the fact that it actually uses these two is maybe the reason, you know. But I said, hold it. Why don't I just put in a hyperbolic cosine where there's a cosine and a hyperbolic sine where there's a sine, see what happens. When you do that, you get 4 of the terms right on. That's great. But you also end up with 2 terms missing and 2 terms that are extra. They are all about the hyperbolic sine. So I said, well, what if I try and add in the right thing and subtract away the wrong thing? And it didn't take long before I found a combination of just these 2 things, the vector that's going in, and hyperbolic sines, hyperbolic cosines in the right orientation. There's the official answer there. So to get rid of the extra terms, you kind of put the hyperbolics right next to each other, play some games with some conjugate operators, and boom, you're done. So I think this is significant because it eliminates a perfectly valid critique of working with quaternions. Now there is an elegant way to represent the Lorentz group using quaternions. Thank you very much.